while I'm waiting for some of the other people to log in, this is my week to be kind of disorganized. I am still in the process of uploading some things for next week's lab that involves solutions and enthalpy of vaporization. All of those things are coming over the next couple of days. I just need to kind of get it all organized and uploaded, and especially the solutions one, which is not an in-person lab. I loaded one video for it, which actually is somebody else's video. And I need to find out from one of my colleagues if they have a video of the part A, because I'm not absolutely sure if Mr. Wheaton actually recorded a version of that last semester. So I'm still working on that project. Like I said, this is my week to be a little on the disorganized side. I'm still missing a few people from my list over here of logged in people. Since homework is supposed to be submitted by midnight tonight, are there questions regarding the intermolecular forces homework? Hopefully, maybe we covered all the pieces for all the major calculations and all that go with that. And I'm dawdling, hoping my other two people will come in. I also have some videos from lectures that I am in the process of getting crunched so that I can post those. So those will be coming also if you need to rewatch something. I'm working on that. So yeah, disorganization hits again. All right, well, I guess I will segue over to the solutions document of notes, and we'll kind of get going on that, and we'll see if my other couple of people show up. On Tuesday, right there at the end of class, we went through those first couple of examples that are provided about percent by mass / mass per volume. And that kind of was the first portion of our how to do different concentrations. So now we're going to leap over to the next thing, which is mole fractions. Mole fractions are usually covered oh so very briefly as part of the gas laws chapter in first semester. You see a little bit of them often in relation to Dalton's law, but that's about all the deeper the first semester gets into it. So this semester now we are doing far more number crunching involving the mole fractions. Mole fractions are a ratio thing. We've got moles of solute that are in the solution to the total moles of both things. So usually this means you have two different mole fractions. And the font that I picked, the New Times Roman font that I used when I typed up the notes, it looks just like a capital letter X. If you use a different font, or if you look in the textbook, sometimes you will see that the symbol used for mole fractions, also known as a chi, it is more along the lines of a cursive letter X, just in case you run across this and think it's something different. No, it's kind of font dependent. When you're doing calculations, you need to look at both components of your solution here. So I've got a couple of different versions of how we're going to sort of crunch our way through this. Well, if you put antifreeze in water, so liquid in a liquid solution, antifreeze is known as ethylene glycol. We didn't specifically talk about glycols as a subcategory back in the organic chapter, but just to give you some hints here, the eth, remember eth means 2 carbons, and the OL should kind of be your tip off that there are alcohols involved in this particular molecule. So if we've got, oops, as I hop around with my cursor here, we've got 1¼ moles of antifreeze, the ethylene glycol. We've got 4 moles of water. So set this up as a fraction that has the thing you are looking on, so chi or x of Eg is my shorthand for ethylene glycol there, goes on the top, the 1¼ add the 2 number values together on the bottom. So we've got 1.25 plus 4. Crunch your numbers. Your mole fraction for the ethylene glycol is 0.238. You always have another mole fraction for the thing that is your solvent. So in this case, we've got chi of water, and the bottom stays the same. The bottom of your fraction does not change. It's still both items added together. This time, however, we are putting the 4 on the top. Crunch it, do your math. We get 0.76. Now, one of the things that you will notice is if you begin to look at also other examples that are in your textbook, if you add the mole fractions of both parts of your solution together, you should get approximately 1.0. Okay. It should look like almost as if you were doing a percentage style problem where you didn't multiply by the 100%. So instead of getting 100 as the value for your 2 numbers added together, you get 1. However, I will, as we sort of progress here, tell you that most of the problems, most of the typical kind of like end of the chapter problems sort of thing, don't usually give you your information in moles. Most of the time, information is presented in grams. So this means you're going to have to do a little bit more math. 60 grams of water, and I'm going to add to it 10 grams of sodium hydroxide. So water is my solvent. The sodium hydroxide is my solute. I want to calculate a mole fraction for each one. But that also then means I need to calculate the moles. Water, 1 oxygen, 2 hydrogens, has a value of 18. And this is another thing where I realize as I'm doing this that I probably should have gone back and put my unit in here. This is actually supposed to be 1 mole on the top of each of one of those fractions so that everything cancels out correctly. So my 60 grams gets divided by the molar mass of water, which is 18, gives me 3.33. 10 grams of sodium hydroxide, slightly bigger molar mass of 40. That gives you a quarter of a mole. The rest of it gets set up a lot like the problem above. Put the number of moles of your item that you're looking at, in this case I happen to do the water first, on the top. Put the two items added together on the bottom, do your division, and you get 0.93 for water. The first example is a little bit more equal in that my water value wasn't vastly different from my number of moles, or my mole fraction for my ethylene glycol. That's actually unusual. The latter example here is probably a little bit more common. If you have a water-based solution, you will often find out that the mole fraction of your water is quite a bit bigger. So 0.93, it's a lot closer to that 1.0 value. The mole fraction of my sodium hydroxide, number crunching wise, turned out to be 0.07. Again, kind of go back and double check, add your two values together. 0.93 plus 0.07 gives you 1. I'm gonna have a look here for a moment at molarity. This should be more familiar. This was something that was covered in quite a bit more detail in first semester. But again, to sort of refresh your memory, since you probably haven't seen it in a while. Molarity, capital letter M, moles of solute per liters of solution. Sometimes then also just abbreviated as MOL over capital L for liters. So if you had a 1 molar solution, what this is telling you is that you would have dissolved 1 mole of something in your 1 liter of water. So again, my spacing here is like really flaky. I did an example here that involves copper sulfate and not a full liter of water. So I've got 5 grams of copper sulfate, and I'm going to put it in 100 mils of water. Unlike doing my percent by mass, this one's a little bit more like my mole fraction, because I need to know how many moles of solute I'm dealing with. Copper sulfate has a molar mass of 159.61. So set up there, we've got 1 mole over that value. So 5 grams is essentially divided by your molar mass, and you get 0.031. As your second step, and you could actually do these side by side. I did them as two separate steps. You could link them together and make the units cancel out as you go across. It would not make a difference in your math. I'm going to divide by 0.100 liters. So that's my 100 mils. Note, I moved my decimal place. So finish out your math there. I get 0.31 molar solution. What if you're going back in the other direction? What if instead of you have a mass and you have a volume and you're trying to figure out what the concentration is, what if you're trying to figure out the concept that you have a particular volume you want, but you actually know the concentration? This is one of the things that I would do if I'm prepping lab. If I'm trying to figure out, oh, well, I need 250 mils for the people I have in lab that lab period, and I want it to be a particular concentration, I'm going to multiply volume. Note, I moved my decimal in this one also. Instead of 250, it's 0.250. Time is my molarity. This allows your liters to cancel out and you are left with moles. And this is another one that I did in 2 steps. You could link your steps together. My molar mass of calcium chloride is 110.98. So I would weigh out 11.098 grams. And since I'm trying to make my notes a little bit more visual, since we're kind of condemned to this method, I found something that I like the looks of. So you could see actually kind of what this looks like when you make it. Not that calcium chloride is orange. Okay, calcium chloride is actually white. But this item that's here in the picture is known as a volumetric flask. You may have occasionally seen them sitting around the lab. Like I said, I sometimes do prep for labs. Sometimes Dr. McHugh does it. This semester, he has lab right before I have lab. So sometimes he ends up making up additional amounts of stuff before he leaves if he thinks that my class is going to run out. But you also have to look at the fact that it has a label on it. Okay, the label there says 100 mils. Volumetric flasks come in a batch of different sizes. They run all the way from sort of Barbie sized, 5 to 10 milliliters, all the way up to, I think the largest one we keep around are the 2-liter size. Now, granted, they're not available in every single volume. It's more selected volumes. So 5, 10, 25 usually is the next one, 50, 100, 250, half a liter, 1 liter, 2 liters. So you have kind of limit as to what you get to choose from. But if you kind of squint a little bit at this picture here, you may be able to notice that looks like there's a little hint of a mark right where the red liquid is at the top of the neck there. And each of these volumetric flasks is engraved with a mark so that you know where, in this case in the picture, where the 100 milliliter mark is. Because it's not fill it all the way up to the top. It's fill it up to the mark. Okay, it makes a difference. Now we hit a different one. This one we haven't seen before. A little bit different spelling. This one is known as molality. And the top of the way it's set up actually kind of looks the same. We've got moles of solute on the top, but note the bottom is different. We have kilograms of solvent, not solution. So not only do we have a slightly different unit, we also are narrowing it down, and it's not whole solution. It's actually just the solvent itself. Most textbooks use a lowercase m when they are doing this as an abbreviation. Usually I'm right on the board when I'm given these kinds of lectures, and it becomes harder to tell, handwriting, capital letter M's versus lowercase m's. I guess that's one minor advantage to doing this digitally. All right, let's have a look through an example or two of this. So if I had 5 grams of potassium iodide, and I want to put it in 5 grams of water, the same sort of step is being done as your first step. I need to convert my grams over to moles because, literally the definition says moles of solute on the top. For potassium iodide, I have a molar mass of 166. So I'm going to do 5 grams divided by my 166 gives me 0.03 moles. Set it over top of, so again, I'm moving decimal places here. It was 500 grams, but I need it to be in kilograms. So I am going to move my decimal and make it half a kilogram. Finish your division, and you get 0.06 molal. What if you needed to figure out how much volume you had to add? So kind of variations on a theme here. If I have 9 grams of oxalic acid, H2C2O4, this is just one of your diprotic acids, and I want to make 0.025 molal solution. Okay, this kind of is a variation on how you're using the definition. So this time I still know indirectly how many moles I've got, because 9 grams oxalic acid has a molar mass of 90. I have a tenth of a mole. But it's the kilograms I don't know. So I had 0.1, and again, this is one of these things where I probably should have written my unit in here. So 0.1 moles over my unknown number of kilograms to give me 0.025 molal. Do your little algebraic switch. Since my kilograms is on the bottom, but my molal on the opposite side of the equals is essentially over 1, I can flip-flop the two of them. And 0.1, in this case, it ends up being mole over 0.025 molal gives you kilograms. I would actually have to have 4 kilograms of water. We kind of are familiar with the concept that 1 milliliter is a gram. Therefore, unless you have greatly altered temperatures, 4 kilograms is 4 liters of water. Now there's one more here that doesn't get used much outside of the medical community. Okay, normality, which is sort of, again, a little bit of a variation on a theme here, is something that gets used a lot more in acids and bases, but more also specifically in medical journals in terms of ionic items. So potassiums, chlorides, carbonates, things like that, things that have a charge to them are often used or given a normality version if you're talking about medical stuff. What we're looking at here is known as equivalents per liter. Okay, think about an equivalent as a thing with a charge. So this is also why acids often get talked about when we're talking about molarities versus normalities. And if you had 1 mole of HCl having just a single hydrogen in it, that would be the same as saying I have 1 normal hydrochloric. If I look at sulfuric, which is the one above it, 1 molecule of sulfuric gives me 2 hydrogens and a sulfate too, but I'm only actually interested in the hydrogens. So because there are twice as many hydrogens as full molecules, this gives you a ratio. 1 molar is 2 normal. If you're talking about something that has 2 hydrogens. And then my bottom example there, phosphoric acid, H3PO4. Okay, you have a 3-to-1 ratio going on here because 3 hydrogens in that molecule. A 1 molar solution of phosphoric acid is going to give you 3 normal. We talk about normality a little bit, but not extensively. This is one of these things where you probably may eventually see a single test question on it. It's something that does exist and you need to be aware of it, but chemists as a whole don't use it a lot. All right, let us blend some things. What if you started with 1 concentration and you needed to be able to find that same solution in different kinds of concentrations? So one of the things that's happening here is if I had 1.22 molar, note capital M, of sucrose, C12H22O11 is sucrose, table sugar. And I wanted to figure out what it was in molality. Well, one of the things that's true about this is I need an extra piece of information. So note the third line down there, I have a density. This tells me that my solution, once it's already made, has a density of 1.12 grams per milliliter. Well, why do I need that? Okay, it's a piece in the puzzle. It also helps you to use that information and extrapolate to, well, what if I had a liter of this stuff instead of just a milliliter? It makes life a lot easier to pretend you have a liter. So look at your density there, 1.12 grams per mil. I'm gonna find out how much my liter weighs. Multiply by 1,000 mils per liter. Obviously, your milliliters cancel out. So if I had a liter of this stuff, it would weigh 1,120 grams. Makes it a little bit easier to do the math for the rest of it. Well, I also know that 1 liter, based upon definition, has 1.22 moles of my sucrose in it. I added up all my number values for all 12 of my carbons, my 22 hydrogens, my 11 oxygens. I have kind of a heavy molar mass there, 342. So 100 or 1.22 moles is going to give me 417.24 grams of sucrose. So remember, all of my solutions have 2 parts to them. They have the thing that you added to it, your solute, and they have the thing you put it in, your solvent. I knew how much the whole thing weighed, because that's why I needed my density. Figure out the mass of your solute and then subtract. 1,120 total solution minus 417 solute means that in that beaker full of stuff, I have 702 grams of water. Now I can make my change over to moles per kilogram, because it said calculate molality. The 1.22 didn't change. It's still the same number of moles of solute. In this case, my sucrose is my solute. But the bottom is different. The denominator of my fraction there, it's not a liter anymore. It's 0.703. Yes, I rounded slightly. 0.703 kilograms. So my molality is 1.73. Now, one of the things you will notice is, again, if you look at my examples versus some of the textbook examples, you'll notice a little bit of a pattern. Most of the time, not all of the time, but most of the time, your molality compared to your molarity for the same solution is a slightly higher number. So look at my two values here. I had 1.22 molar, but I've got 1.73 molal, okay, molality. Little bit higher value there. Okay, pursuing down this like a theme. Okay, what if I wanted to know my percent by mass? I have info. Okay, I know that my sucrose, by my previous calculation, is 417. I know that my whole solution is 1120. Divide, multiply by 100, and I get 37.3% by mass. Keep going. What about my mole fraction? Again, I'm hanging on to one of those numbers. The 1.22 hasn't changed. I still have 1.22 moles. I do need to know how many moles of water I have. Remember I said earlier that it typically tends to be a situation where the solvent, in this case, the water, tends to be way more compared to my solute. So I have 702.76 grams of water, molar mass of 18, about 39 moles of water. That's an awful lot. It also means my mole fractions are super lopsided. My mole fraction for the sucrose, abbreviated SUC there, is really small because it's 0.03. The 40.26 is 1.22 plus 39.04. That's where I got that value. The mole fraction of my water is way closer to 1. It is 0.97 by the time you finish your math there. So homework problems, okay? Homework problems that are coming. If I give you information about concentration, I kind of also have to give you a density. Otherwise, you are missing a piece of the puzzle in order to be able to do all the different conversions. We're also going to do remember I said I haven't got quite everything loaded up for the solutions lab that is just a simulation. It has one video that involves solubility that I did actually load that about half an hour ago. So you can watch that. I need to find out from Mr. Wheaton if he has a video that kind of shows a physical execution of figuring out solute versus solvent from a lab situation. But that may be coming, so I will let you know about that on Tuesday probably. All right, we're going to switch gears a little bit. Still solutions, though. That's what the chapter's all about. This has more to do with, okay, let's pretend we have a nice, fun scanning tunneling microscope that allows us to see at the molecular level. how do you make a solution? What's sort of involved both thermodynamically, but also from a kind of a visual point of view here? In order to get your solution to form, we're going to have three main parts to it. Okay, the first part involves when you dump your solute into the water. Okay, think dump that sucrose into the water. Okay, all those little minute cubes that are your sugar actually have to begin to separate into separate molecules. So in this case, we have, I believe it's labeled in my picture that I stole from somewhere on the net. It says solute crystal. They're the blue ones at the bottom of the picture there. So as they begin to separate from each other, you note that you see the little arrow there, and then it shows the same little blue dots, but they're further apart. Okay, this is an endothermic process. Takes a little bit of energy in order to kind of spread them out. Look at the little red dots. Okay, the little red dots represent separation of the solvent. It's got a lot of similarities, okay, in that they are much closer together in the beginning and they become further spread apart as you are creating the solution. This is also an endothermic process. Now, the final step involves mixing them together. Now, this is kind of hit or miss in that some things are endothermic, endo for endothermic, and some things are exothermic. In the first semester of chemistry, we do a lab referred to as calorimetry. I know a few of you did actually have me for the first semester, and I usually do it as a demo. You take a solid and put it in the magnificent styrofoam coffee cup calorimeter with some water, and you stir it carefully with a thermometer, and the temperature either goes up, indicating it's an exothermic reaction, or down, indicating that it's an endothermic reaction. So it depends upon what actually you're dissolving as to which one it is. Since we're supposed to get snow again tomorrow night, yay, I'm not sure if I'm thrilled about that or not. Road salt is not actually salt like you put on your food. Okay, it's not sodium chloride. Road salt is calcium chloride, CaCl2. Calcium chloride has multiple benefits, and we'll circle back to this idea again later in the chapter too. One of its benefits is when you put calcium chloride in water, okay, if it's wet, soggy snow hitting the surface of the pavement, there's some liquid there now. You add the road salt, you get an exothermic reaction. Calcium chloride in water creates heat. So if it was beginning to freeze on the surface of the pavement, the heat would lead it to melt some of that back away. There's another facet to this that we'll talk about later called colligative properties. But the fact that it's exothermic is one of the bennies there. All right, some more conceptual stuff here. So solubility has a couple of guidelines. One of them being that like dissolves like. A couple of words that it's, again, sort of are pulled from first semester, polar and nonpolar. Polar things like to dissolve polar things. Okay, so salt, which is so polar, it's actually ionic, table salt, sodium chloride, dissolves well in water because like dissolves like. Non-polar dissolves non-polar. Okay, so things that are heavily carbon and hydrogen aren't going to be polar, because this goes back to the whole concept of, remember hydrogen bonds from the last chapter. Polar things tend to have O's and H's as well as C's. So, and N's too. Again, more words here. Hydrophilic. Let's go sort of Greek here. Hydro means water, philic means loving. So hydrophilic is water loving, or something that is polar, something that is going to mix well in water. Things like, okay, think about things that we saw back in the organic chapter. We saw alcohols, OHs. We saw COs, ketones and aldehydes. We saw amines and amides too. All of those, depending upon how many carbons are actually involved, are pretty good at dissolving in water. Non-polar, more Greek stuff here, hydrophobic. Yes, I know that sounds like they have rabies, but means water fearing or not going to mix with water. You get carbon-carbon single bonds, things that are alkane-like. You get carbon-carbon double bonds. You could also potentially have some triple bonds in there too. And you get some carbon to hydrogen bonds. Note, we're missing O's and we're missing N's. We're missing things that are fairly electronegative. Carbons and hydrogens are a lot less electronegative. So let me tell you a little tale. My husband shipped from the UK to Virginia Beach a yard. Okay, if you have ever gone to the UK, or also if you've ever gone to Vegas, a lot of times when they sell alcohol, they sell, and we'll see if I can make this draw with any sort of recognizability here. Draw, okay. Okay, a yard has kind of an oval top to it, and it's long and skinny, and at the bottom it's got kind of a bulb-shaped end of it, and it comes back up here. And you fill it with beer, okay? The idea being that, okay, here's your liquid, and the idea being that you can't sit it down because it's round on the bottom. Granted, the ones they sell in Vegas are sometimes flat on the bottom, but yards, as in a yard of ale, or if you are aware of, there is a place called the Yard House in Virginia Beach, which is in the town center area. They that's sort of their trademark. They have some of them hanging around. Okay, so think about the shape of this thing. Okay, up here at the top end, it is much wider than it is down here at the bottom end, right before you get to the ball. So my husband, in shipping a yard of ale to somebody that he knew back here in the States, this is when he lived in Wales, stuffed it full of styrofoam peanuts. So styrofoam, completely uneco-friendly, not biodegradable styrofoam, is mostly carbons and hydrogens, okay? Which means putting it in water doesn't do much. You could add water to this styrofoam peanut stuffed object here. Wouldn't help a lot because it would only float out the few that are up near the top. It doesn't help with the ones that are down here at the bottom that are like stuck in the ball part. So I had to convince the recipient to go out and buy a couple bottles of nail polish remover, i.e. acetone, which is a non-polar solvent, and use the acetone to dissolve the styrofoam peanuts such that he could get them out of the yard of ale and later be able to use it for drinking purposes. So there is usefulness in chemistry. I have used my chemistry knowledge to do all sorts of really oddball things, to dissolving styrofoam in a yard of in an ale yard, stripping wallpaper off my really evil looking kitchen wall back before we redid our kitchen. I ended up using sodium hydroxide to remove the wallpaper because everything else I tried didn't work. And in the rule of, this is not exactly like dissolves like, but when you're cleaning glassware, the first rule is try a non-toxic solvent like water or alcohol. Then progress onward to acids. I tried vinegar. You can't, unless you're buying muriatic acid from Lowe's, you can't buy much stronger acids commercially. But sodium hydroxide is oven cleaner. So I ended up using oven cleaner to take my wallpaper off. That was a really interesting adventure. All right, let's go back to solubility. All right, 2 more words, okay? 2 more words that you need to be aware of here. Miscible and immiscible. And they're kind of actually what it sounds like. Miscible is mixable. If you say that isopropyl alcohol is miscible in water, okay, yeah, water dissolves, rubbing alcohol, it mixes with water. Immiscible, okay, if you have motor oil and you spill it in a puddle, a rain puddle, the 2 things are not going to mix because motor oil, which is mostly a petroleum product, is not going to mix with the water. More solubility effects. So pressure does not affect solubility of liquids and solids very much. Slightly, but not much. Gases, on the other hand, are actually highly subject to pressure. So the rule that guides this is known as Henry's law. So look at what it says there. We've got amount of gas dissolved in a solution is directly proportional to the pressure above the gas. So look at my equation here. I've got S sub G, that's my solubility. K with the little h is a constant, and it would be different for every gas. And P sub G is the pressure of the solute. So more pictures to kind of help you think about this a little bit. If you have higher pressure, your soda can is still shut and you have not opened it yet. The fact that the carbon dioxide is pressurized in the bottling process means that there's a fair bit of carbon dioxide dissolved in your soda while the pressure is still high. So crack the can, twist open the lid. If it's a bottle, you hear that sound, which means you are releasing pressure. Air pressure around here is pretty much always 1 atmosphere because we're at pretty much sea level. When it's bottled, it's about maybe 1.5, 1 3/4 atmosphere. It's pressurized enough that there is a distinct difference between the never been opened soda container and after you have opened it, and especially after you've left it open for an hour or more. All of that gas that was pressurized down into the liquid is now escaping. So look at my little picture here. The one on the left implies that there's relatively high pressure. Most of the gas is, it's like you actually, no, I said that wrong. The one on the left is actually low pressure, because there's not a lot in the liquid, and there's also not a lot above the liquid too, because it's already escaped. The one on the right is the high pressure one. We've got quite a bit of gas molecules in the liquid, but we also have quite a few that are basically trapped in the space between the liquid surface and the top of the beaker. And yeah, this particular picture doesn't show you with an obvious seal or a top on the beaker, but the idea still holds true. All right. What else affects solubility? Temperature. This is another situation where solids and liquids tend to behave differently than gases. For the most part, solids and liquids dissolve better in warm liquids. Look at some of your lines here. For instance, the green line labeled KNO3 is one that is going to be talked about more in the solubility lab. It has kind of a gentle but relatively steep curve going upward. You've got sodium chloride, which, okay, at 0 degrees Celsius, we've got about 35 grams that will dissolve in 100 mils. At 100 Celsius, we've got about 40. There's not a huge difference in salt solubility in water. It dissolves really well. If you look at the K2CR207 one, that's another one where there's not a lot of solubility at the cool temperatures, quite a bit more at the hot temperatures. All right, being that this is the South, if you want to make sweet tea, and why anybody would drink that stuff is beyond me because I think it's gross as hell. If you want to make sweet tea and you want to put all the sugar in it, usually what you do is you boil the water, put the tea bags in, let it steep for a little while, pull the tea bags out, and while it's still relatively hot, stir your multiple cups of sugar into the pitcher, because the sugar dissolves more easily in the warm liquid. There's exceptions. If you look all the way at the bottom of this graph, there's this oddball compound there, cerium sulfate. Cerium is an inner transition metal. Not a lot of uses except in ceramics. It also behaves kind of weirdly in that it is slightly more soluble in cool temperatures than it is in the hot temperatures. So again, it's not an absolute rule. And looking at all these different colors and all of these different substances, all the different colored lines there, some of them have big differences between hot and cold. Some of them, like sodium chloride, have much smaller differences between hot and cold temperatures. Gases are backward. Gases decrease in solubility with increases in temperature. So different graph here. We've got helium. Okay, helium, for one thing, is not super soluble to start with in water to begin with anyway, and changing the temperature doesn't seem to make it a whole lot better. It's not quite exactly a flat line, but it doesn't have an awful lot of a curve to it. Nitrogen, okay, definitely, okay, little bit more of a curve to that one. The cooler temperatures, we've got around, this is 10 to the negative third per mole, so about 1,000th of a mole per liter. Carbon monoxide, methane is actually pretty darn water soluble. If you're looking at that top line there, that's sort of golden color. Cool water and methane are a pretty good combo, which also, if you have hot springs, not that we have a lot of that in this area, more like, think Yellowstone. Methane as well as hydrogen sulfide are produced in the hot springs in the Yellowstone area. But as you get hotter, you get less solubility. You kind of, it's backwards. It's different than you would expect, but gases tend to be backwards compared to liquids and solids. In fact, sometimes factories that discharge just hot water, there are certain types of industries that, although they're not discharging a toxin into rivers and streams, sometimes the fact that they discharge hot water into bodies of water like streams and lakes and all of that will sometimes cause fish kills because there's less oxygen in the water. Therefore, the fish have problems. So all of these things have kind of different levels of relevance in terms of all the different ways you can tinker with your solubility. So the last thing that we are going to start on today, this won't get finished until next week, is colligative properties. Colligative properties, again, are probably not exactly the way you think they will influence things. Colligative properties depend on how many particles and not what they are up to a point. So you could dissolve salt in water, you could dissolve sugar in water, you could dissolve the potassium nitrate in water. And if you had 1 mole in your liter for each of those substances, the way the colligative properties work is not going to be different because it's not about what they are, it's about the how much. So the ones that are usually covered in general chem, we've got 4 major ones, and 2 of them are very closely linked to each other. The first one is known as vapor pressure lowering. The 2 middle ones, boiling point elevation and freezing point depression, are very, very tightly linked. And the last one, osmotic pressure, is definitely less linked to the other ones. So we'll talk a little bit about the vapor pressure today. We have to specify a couple of things. We want to think about the vapor pressure, which we talked about vapor pressure a little bit in terms of Clausius-Clapeyron, how if you have a sealed container and you allow it to come to equilibrium, you get this situation where there's a ratio between how much is in the liquid and how much is above the liquid. So one of the things we got to do about this, however, is assume that the solute that we are dumping in our solvent is non-volatile. Okay. Volatile means has a tendency to evaporate. Glade plugins, the little thing that you stick in the electrical socket in your room, I think they smell awful, but people buy them. It's this little bit of liquid. It's like about a tablespoon worth. And the reason why you plug it into your electrical socket is it provides a very small but constant amount of warmth to cause your liquid to volatilize. So we want to mix something into our solvent that doesn't turn into a gas. If you mixed isopropyl alcohol into water, this wouldn't quite obey these rules because isopropyl alcohol evaporates given time. So we're going to assume that it's a non-volatile one. What it does is it lowers the vapor pressure. I thought this was a pretty good picture here that kind of goes with this. Think about it in terms of, okay, if you have the pure solvent, okay, obviously there's atmospheric pressure above it, and every molecule of your solvent that actually makes it up to the surface tension and all of that, and has enough energy is capable of escaping. What if you put stuff in your solvent? Let's take our water and put sugar in it. Okay, stir a couple of tablespoons of sugar into it. Well, the sugar molecules are not volatile, and they kind of sort of get in the way. Not as many solvent molecules make it up to the surface and escape. And so this is why you get a lower vapor pressure for a solution than you get for a pure solvent. So next week, we're going to get into Raoult's law and how this influences your vapor pressure lowering and how you can do the math for it. So that's kind of where we're going to pick up for Tuesday. Since I know I had a couple people log in late, since homework for intermolecular forces is due tonight, are there any questions that apply to that homework that you got stuck on, anything that you need to ask me? No? Okay. I have already posted the homework set for solutions. If you have free time over the weekend that you are studying and that sort of thing, you can begin to look, because we've covered some of this. We've covered a little more than half the chapters, so you might want to take advantage of the weekend to finish or to start your homework for solutions, because we're going to finish up, probably going to finish up the rest of the chapter on Tuesday. I'm not sure. We'll kind of see how it goes. But let's just say it's probable that we will finish the solutions chapter on Tuesday. We have 3 sections left to go. All right. I will see you on Tuesday.